Well, since the last time that we met together over video, you have had a chance to actually have some experience with a mass and a spring. And that experience may have been with an actual physical mass and spring, or it may have been in an online simulation. But hopefully what you discovered through that experiment was that it didn't make any difference how far you displaced the mass from the spring, whether you displaced it a little bit, whether you displaced it a whole lot. The period of the vibration of that spring turned out to be the same if you didn't change the spring. Hopefully you didn't change the spring as you were working through that laboratory exercise. So this is the point where I want to get in here and talk about the restoring force in order so that all this, we can get all these terms together in one spot and hopefully all of it starts to make some sense. So here I have a drawing of supposed to be a mass on a spring. And so the black section right here is where it would be hanging if it was not moving. And so this is the equilibrium position of the mass. Once you displace it, once you pull it down, the amount that you pull it down is going to be the amplitude. Because once I pull it this far and then let go, it's going to keep bouncing back and forth. It's not going to go any lower than I pulled it. And so that's the maximum distance here. And even though the online simulation, if that's what you use, it may not have quite looked like this, the amplitude on the bottom and the amplitude on the top should have been the same, because it's going to go up the same distance on the top as it is from the bottom. So that's the maximum distance from equilibrium, and so that's represented by this green arrow either here or here. Now the period is how long it takes to make one complete cycle. So if you start timing from here and you go all the way up and all the way back down, that's a period. Or if you started timing it when it was at the top and you went all the way down and all the way back up, that would be a period. Or if you started in the middle and then it went down and then up and then back to the middle, that's still a complete cycle. The complete cycle means it has to go both down and up and get back to where it started from. Now, you'll also want to keep in mind that when we talked about uniform circular motion, we also talked about frequency and how frequency and period were reciprocals of one another. And you will need this equation again in some of the problems that you're going to be working in this section. So I just wanted to throw it in there to remind you of it. This particular kind of motion is called simple harmonic motion. Simple harmonic motion is periodic motion, but it has a couple of very specific types of criteria that go along with it. First of all, the period is independent of the amplitude. In other words, it doesn't matter if I pull it down this far, it doesn't matter if I pull it down this far, if I pull it down this far. The time it's going to take to make a complete period is going to be the same no matter how far I pull it down. So the period and the amplitude are independent of one another. Secondly, in order for there to be simple harmonic motion, the restoring force is going to be proportional to the displacement. Now, let me try to show you what I mean by that. So, when it is at the equilibrium position, it is just sitting there, assuming that it is not in motion, it's just sitting there. If you remember the problem that we did in the previous video, we said that the weight of the mass was going to be equivalent to the restoring force of the spring, and so it was in equilibrium, then that means there was no net force on it. Now, once I pull the mass down here, the spring wants to try to pull this mass back up to the equilibrium position again. And so down here is where there is a force that is going to be applied. And the spring is going to keep applying a force until it gets back up to the equilibrium position again. Now, when it's down at its maximum distance from equilibrium, the restoring force is going to be at its maximum as well. As it gets closer and closer and closer back to equilibrium, the restoring force becomes less and less and less. So the restoring force is a force that is constantly changing. It is not something that is the same amount of newtons every single place in the journey of this mass as it's going back and forth on this spring. Because here it's at a maximum. The closer I get to this, the smaller the restoring force becomes, as the spring is trying to pull it back to equilibrium. Now, if you think about the top portion of the journey, it's the same thing up here, because down here the spring is stretched, but up here at the top, the spring is actually compressed and it's trying to push the mass back to equilibrium. So again, at this amplitude, the restoring force is at its maximum amount, and the closer it gets to equilibrium, the smaller that restoring force becomes. So here, the restoring force is at its maximum amount, and at equilibrium, the restoring force is equal to 0. All right, that's what I mean when I say the restoring force is proportional to the displacement. The greater displacement, the more the restoring force is. The less the displacement, the less the restoring force is. Now, you should also remember our old friend Newton's second law, F equals ma, and we know that the force and the acceleration are proportional to one another. And so if the force is at its maximum, that means the acceleration is also going to be at its maximum, okay? And when I get up here, if force is 0, that means acceleration is going to have to be 0 as well. I'm going to go ahead and throw this other piece in here. We won't talk about it a whole lot until we start talking about energy. But at this particular point, when we are changing directions, the mass has gone down, and then it's going to change direction, and it's going to go back up. There is a particular point in time right here where the velocity is 0. And so at the amplitude, the velocity is 0, and then the closer and closer and closer it gets to the equilibrium position, the mass gets faster and faster. So here, you could be thinking, well, if the force is 0, why is it going to keep going up? Well, that's an energy discussion that we're going to get into in the next section. But it's going to keep moving because it's got velocity right here, and the momentum is going to keep it going up to the upper amplitude. So the velocity is 0 at the amplitude. The velocity is going to be at its maximum when it gets to its equilibrium position. So you want to keep in mind these relationships with relation to what position the mass is in at different parts in its journey. All right. Now we are going to look at example 10.3. It says a student hangs a spring from the ceiling. She then hangs a 34.5 kilogram mass on it, and the spring stretches 59.1 centimeters. So let's get that information up here. The mass is 34.5 kilograms, and the amount that the spring stretches is going to be 59.1 centimeters. And I learned from the problems that I did before that this is going to have to be a meter, so it's an SI unit, so all my units match. So let's go ahead and change that. That's going to be 0.591 meters. And this is the case once the spring is actually stretched, once I've hung the mass on it. Okay? Then it says, after the spring has stretched to its new equilibrium position, so this point right here, once the mass is hanging on it, the student pulls the mass down an additional 35 centimeters and releases it. So my new delta X is 35.0 centimeters, which is the amount I've pulled to start the motion. So we'll get that information up here as well. And the question is, what will be the period of the resulting motion? Okay. Now, you know from reading the section that in order to find the period is equal to 2 times pi times the square root of m over k. Well, I know m, and I certainly know what pi is, but I don't know what k is because I don't know what this spring constant is on the spring. So therefore, the first thing I've got to do is I've got to figure out what k is. So k can be calculated by using Hooke's law. So I have F equals negative k times delta x. How do I get what this force is? Well, we talked about this before. We said the force is going to be equal to the weight. So the weight is equal to the mass times the gravity. So the mass is 34.5 kilograms times gravity, which is a negative 9.8 meters per second squared. And that is going to give me, where did I write it? A negative 340 newtons. Okay, so weight is negative 340 newtons. That tells me that the force then is going to be a positive 340 newtons, because remember, they're equal in magnitude but opposite in direction, because at equilibrium the forces are, there is no net force on it. I don't know what K is, and delta X is going to be the amount that this was going to be stretched. So this is going to be 0.591 meters. So when I solve this for K, that is going to give me a K equal to 580 Newton meters. So now I have K, now I can actually go in and calculate the period. All right, I'm going to have to make a little bit more space here. So I've erased part of that, but that's okay, because you remember what was there. So I have 2 pi times the square root of m over k. So the period is 2 times pi times the square root of the mass, which is 34.5 kilograms. And then I have k, which is 580 newtons per meter. Now that looks like an absolute mess of units down here. So what am I going to do in order to figure out what this is supposed to look like? Well, if you recall, Newton just means kilogram meter per second squared, and all that is over seconds because it's actually, it's over meters because it's Newton meters, newtons per meter, and so that's what the units look like here. When I look at this, my kilograms both cancel out, my meters both cancel out, and then I have seconds squared in the denominator, and so that's actually going to flip over because it's in the denominator twice. It's in the denominator here, and it's in the denominator because of this denominator right here. That's going to flip it over, put it in the numerator, and when I solve that, it's the square root of seconds squared, which is going to give me seconds, which is what I should have. So when you take 34.5, divide it by 580, then when you get that division result, you need to take the square root of it, multiply it times 2 and times pi, and you should get a period of 1.5 seconds. Now, I want you to notice, I didn't use this. They gave me the information, but I didn't need it because, as you've already learned, it doesn't matter what the amplitude is. It only matters what the spring constant is doing and what the restoring force of the spring is. The period is independent of the amplitude. It didn't matter how far she stretched it. The period would have been the same regardless, okay? So that's how you're going to go about working this kind of problem. You're going to use the weight in order to figure out the force on the spring. And if they give you 2 delta x's, make sure that you're using the displacement where the string, or where the spring, not the spring, the string, where the spring has been stretched. Make sure that you're using that displacement and not the one that they're pulling to start the motion, because the amplitude doesn't make any difference, okay? So you use the weight to find the force, and then figure out what the K is for your spring. Once you know what the K is for your spring, then finding the period is easy. If they would happen to ask you what the frequency is, then you can go back and use the reciprocal relationship between period and frequency in order to find that. Alrighty? So you'll be able to get some practice doing that today.